In Section 2 of Chapter 16, we will be discussing precipitation and qualitative analysis. In Section 1, we looked at solids dissolving in solution. Now we will look at the opposite, the ions coming together to form a precipitate. So again, in this section, we will be looking at Q and comparing it to the equilibrium constant. This time we'll be comparing it to KSP. So Q will be calculated in the same way that KSP is calculated, but again, we want initial concentrations to calculate Q and not equilibrium concentrations like we use to calculate the KSP. When we look at Q, or the ion product, and compare it to KSP, we use it to determine if precipitation will occur. When precipitation occurs, we are referring to the reverse reaction, the ions coming together to form the solid. So Q is greater than KSP, that means we have too much product, and the reaction will shift to make precipitate, and then will continue to do so until the concentrations of the ions are reduced to the point where they meet the KSP. If Q is less than the KSP, no precipitation will occur. So let's take a look at an example where we mix two solutions together, and let's see if we get a precipitate. So here's our precipitate, and the cation comes from this solution, and the anion comes from this solution. We've got the KSP for our precipitate, so let's do some calculations. To calculate Q, we need the initial concentrations of our reacting ions. So here's the equation showing our precipitate and our reacting ions. So to calculate the initial concentrations of those ions, we need to realize that when we put the two solutions together, we have an increased volume. And so let's use M1V1 equals M2V2 to calculate the initial concentration for each of the reacting ions. So for the cerium ion concentration, we get 2.86 times 10 to the negative third molar when we use 1,050 milliliters as our V2 for each calculation. The iodide ion concentration, 5.71 times 10 to the negative third molar. These are initial concentrations. We're not thinking about them reacting yet. We're just thinking about what happens to the concentration when we add these two solutions together and they dilute one another. Now to calculate Q, we'll take the cerium ion concentration times the iodide ion concentration cubed according to the balanced chemical equation. Let's plug in the values and solve for Q. We get 5.32 times 10 to the negative 10th for Q. So now we have to ask ourselves if this is greater than or less than the KSP. And in this case, it is slightly larger than the KSP, 1.9 times 10 to the negative 10th. And so we will get a precipitate from this solution. When Q is greater than KSP, we have too much product, we have too many ions, and so then our reaction will shift to remove those ions and make our solid, make our precipitate. Now sometimes we might want to know more than if we get a precipitate or not. Like in this problem, we would like to know the concentration of the magnesium and the fluoride ion at equilibrium. And so this will require a little bit more work. Let's first find the initial concentrations of our reacting ions to calculate Q to see if we get a precipitate. So I used M1V1 equals M2V2 again to solve for the initial concentration of the reacting ions, magnesium and fluoride. And now I can calculate Q. So I take my magnesium ion concentration times my fluoride ion concentration squared, because there are two fluorides in my chemical formula for magnesium fluoride. And my Q value is 1.46 times 10 to the negative fifth. Now that is much larger than the KSP, 6.4 times 10 to the negative ninth, so we do get a precipitate. So now let's think about making this precipitate. I have 1.50 millimoles of magnesium ion. I just took my concentration times my volume for the magnesium, and I did the same for the fluoride, the concentration times the volume for the fluoride ion to get my millimoles. And now I can think about reacting all of the magnesium ion and having an excess of fluoride ion. Notice how I doubled 1.5 millimoles to 3 millimoles here for the fluoride because of the 1 to 2 mole ratio in my chemical equation. So if I divide my 22 millimoles of fluoride ion by the total volume, which was 400 milliliters, I get a new concentration of 5.50 times 10 to the negative second molar. So now we have assumed that all the magnesium ion is reacted, but really at equilibrium there will be some magnesium ion. So let's do our ice chart. My initial concentration for magnesium ion is 0. My fluoride ion concentration is this new concentration we calculated here. And then we say plus X for magnesium ion and plus 2X for fluoride ion. And so at equilibrium, magnesium ion concentration will be X, and the fluoride ion concentration will be 5.50 times 10 to the negative second molar plus 2X. Our equilibrium expression gives us our KSP equals our magnesium ion concentration times our fluoride ion concentration squared. We can substitute in for the KSP and then substitute in for the magnesium ion concentration and the fluoride ion concentration. However, we can simplify this because KSP is so small. We can just say, get rid of this part, and just substitute in 5.5 times 10 to the negative second for the fluoride ion concentration. When we solve for X, we get 2.1 times 10 to the negative sixth. This would be the magnesium ion concentration. However, for the fluoride ion concentration, we would actually want to do 5.50 times 10 to the negative second plus 2x. But we would find that essentially our answer for the fluoride concentration is unchanged, right? It's 5.50 times 10 to the negative second molar. So there are our final answers. Now let's talk about selective precipitation. If you have a mixture of metal ions in solution, you can often separate them using selective precipitation. You use a reagent or a reactant that has an anion that forms a precipitate with a specific metal ion in the mixture. For example, say you had a solution that contained barium ions and silver ions. If you added sodium chloride, you'd get a silver chloride precipitate, but not a barium chloride precipitate. The barium would stay in solution. And so this is how you could separate silver ions from barium ions, by adding sodium chloride. So let's look at a solution that contains copper ions and lead ions. We're going to add a source of iodide, and we're going to see if we can make lead iodide or copper iodide first. And then we will, at the end, look at the concentration of iodide that would be necessary to begin precipitation for each. Let's think about the lead iodide precipitate first. This would be our equilibrium expression. The iodide ion concentration would be squared because we have two iodines in our chemical formula. And we are told that the lead ion concentration is 0.0020 molar. And so we could substitute that in here along with our KSP and solve for our iodide ion concentration. We get 2.6 times 10 to the negative third molar for the iodide ion concentration. Anything in excess of this will cause the precipitate to form. Now let's do the same for the copper iodide. We have the KSP, and we also have the copper ion concentration as 0.00010 molar. So we can substitute that in and solve for our iodide concentration. We get 5.3 times 10 to the negative 8th molar. So any concentration of iodide in excess of 5.3 times 10 to the negative 8th molar will cause the precipitate to form, copper iodide. So this means that as the iodide is added, the copper iodide will precipitate first, since the iodide concentration that is required is less. 10 to the negative 8th is less than 10 to the negative 3rd. So the copper ions would be separated from the lead ions using this iodide reagent. And the final part of the question says to specify the concentration of the iodide necessary to begin the precipitation of each salt. Those are our answers that we calculated here and here. One final thing I'd like to mention is how the sulfide ion is often used to separate metal ions by selective precipitation. The KSP values vary greatly for these metal sulfides, as you can see in the table here. So that is why sulfide ion is often used to separate out metal ions. So let's say we have a solution that has copper, mercury, nickel, and manganese ions. You can see that the manganese sulfide and the nickel sulfide are much more soluble than the copper sulfide and the mercury sulfide. Now remember, I can compare these KSP values because the sulfides contain the same number of ions. Now, if I wanted to separate out, say, the manganese ion from the nickel ion, I could add sulfide and get the nickel sulfide to precipitate out first, leaving the manganese ion in solution. But because I have all of these ions in solution, copper, mercury, nickel, and manganese, I need to regulate the pH of the solution to control the concentration of the sulfide ion to get these to precipitate. The sulfide ion is basic. It comes from hydrosulfuric acid, which is diprotic, seen in the equations here. In an acidic solution with a low pH, the sulfide ion will pick up hydrogen ions or protons, and there won't be a lot of sulfide ion in solution. And so then the copper sulfide and the mercury sulfide can precipitate out. At higher pHs, we have hydroxide added to reduce the hydrogen ion concentration, and then the reaction shifts right, producing sulfide ion. So there's a higher concentration of sulfide ion, and then the manganese sulfide and the nickel sulfide can precipitate out. So by playing with the pH, we can adjust the sulfide ion concentration and then selectively precipitate out the more soluble or the less soluble sulfides. This diagram shows what was just discussed. Having an acidic environment creates a lower concentration of sulfide ion, and so then the less soluble precipitates are formed, and then making the solution basic produces more sulfide ion, and the more soluble precipitates are formed. You can read pages 772 to 774 in your textbook to learn about a scheme used for qualitative analysis which selectively precipitates out metal ions.